Oxidation, reduction, and redox reaction. Oxidation defined as a loss of electrons, while reduction is defined as a gain of electrons. In a redox reaction, both oxidation and reduction reaction takes place simultaneously. Direct redox reaction. In a direct redox reaction, both oxidation and reduction reactions takes place in the same vessel. Chemical energy is converted to heat energy in a direct redox reaction. Indirect redox reaction. In indirect redox reaction, oxidation and reduction take place in different vessels. In an indirect redox reaction, chemical energy is converted into electrical energy. The device which converts chemical energy into electrical energy is known as an electrochemical cell. In an electrochemical cell, the half cell in which oxidation takes place is known as oxidation half cell. The half cell in which reduction takes place is known as reduction half cell. Oxidation takes place at anode, which is negatively charged, and reduction takes place at cathode, which is positively charged. Transfer of electrons takes place from anode to cathode, while electric current flow in the opposite direction. An electrode is made by dipping the metal plate into the electrolytic solution of its soluble salt. A salt bridge is a U-shaped tube containing an inert electrolyte in agar-agar and gelatin. A salt bridge maintains electrical neutrality and allows the flow of electric current by completing the electrical circuit. Representation of an electrochemical cell. Anode is written on the left while the cathode is written on the right. Anode represents the oxidation half cell and is written as metal-metal ion concentration. Cathode represents the reduction half cell and is written as metal ion concentration metal. Salt bridge is indicated by placing double vertical lines between the anode and the cathode. Electrode potential is the potential difference that develops between the electrode and its electrolyte. The separation of charges at the equilibrium state results in the potential difference between the metal and the solution of its ions. It is the measure of tendency of an electrode in the half cell to lose or gain electrons. Standard electropotential. When the concentration of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. It is denoted by E0. Standard hydrogen electrode consists of a platinum wire sealed in a glass tube and carrying a platinum foil at one end. The electrode is placed in a beaker containing an aqueous solution and acid having 1 molar concentration of hydrogen ions. Hydrogen gas at 1 bar pressure is continuously bubbled through the solution at 298 Kelvin. The oxidation or reduction takes place at the platinum foil. The standard hydrogen electrode can act as both anode and cathode. If the standard hydrogen electrode acts as an anode, H2 twice H plus plus twice E minus. If the standard hydrogen electrode acts as cathode, twice H plus plus twice electron product H2 gas. Cell potential is called the electromotive force of the cell EMF when no current is drawn through the cell. None studied the variation of electrode potential of an electrode with temperature and concentration of electrolyte. None formulated the relationship between standard electrode potential E0 cell equal to E0 cathode minus E0 anode. In the electrochemical series, various elements are arranged as per their standard reduction potential values. A substance with higher reduction potential value means that it has a higher tendency to get reduced, so it acts as a good oxidizing agent. A substance with lower reduction potential value means that it has a higher tendency to get oxidized, so it acts as a good reducing agent. The reduction with higher reduction potential acts as a cathode, while the electrode with a lower reduction potential acts as an anode. The potential difference between the two electrodes of a galvanic cell is called cell potential and is measured in volts. The cell potential is the difference between the reduction potential of cathode and anode. Cell potential is called the electromotive force of the cell (EMF) when no current is drawn through the cell. None studied the variation of electrode potential of an electrode with temperature and concentration electrolyte. None formulated a relationship between standard electrode potential E0 and electrode potential E cell equal to E0 cell minus 2.03 RT divided by NF log concentration of anode ion divided by concentration of cathode ion. At equilibrium, cell potential E0 cell becomes 0. Relationship between equilibrium constant Kc and standard cell potential E0 cell. E0 cell equal to 0.059 divided by n log Kc at 298 Kelvin. Work done by an electrochemical cell is equal to the decrease in Gibbs energy. The standard equal minus NF E0 cell. The substances which allow the passage of electricity through them are known as conductors. Every conducting material offers some obstruction to the flow of electricity, which is called resistance. It is denoted by R and is measured in ohm. The resistance of any object is directly proportional to its length and inversely proportional to its area of cross section A. R equal to rho L by A, where rho is called specific resistance or resistivity. The SI unit of specific resistance is ohm meter. The inverse of resistance is known as conductance G. Unit of conductance is ohm inverse or mho. It is also expressed in Siemens denoted by S. The inverse of resistivity is known as conductivity. It is represented by the symbol kappa. The SI unit of conductivity is Siemens meter inverse, but it is also expressed in Siemens centimeter inverse. Conductivity equal to conductance into cell constant. For measuring the resistance of an ionic solution, there are two problems. Firstly, passing direct current changes the compositions of the solution. Secondly, a solution cannot be connected to the bridge like a metallic wire or a solid conductor. Conductivity cell. The problem of measuring the resistance of an ionic solution can be resolved by using a source of alternating current, and the second problem is resolved by using a specially designed vessel called conductivity cell. A conductivity cell consists of two platinum electrodes coated with platinum black. They have area of cross section A and area separated by a distance L. Resistance of such a column of solution given by the equation R equal to rho L by A equal to 1 by kappa L by A, where L by A is called cell constant and is denoted by the symbol G star. Molar conductivity of a solution. It is defined as the conducting power of all the ions produced by dissolving 1 mole of an electrolyte in solution. Molar conductivity lambda m equal to kappa into 1000 divided by m, where kappa conductivity and m is the molarity. Unit of molar conductivity is Siemens centimeter square mole inverse. Coleridge's law of independent migration of ions. According to this law, molar conductivity of an electrolyte at infinite dilution can be expressed as the sum of individual contributions from each individual ions. If the limiting molar conductivity of the cation is denoted by lambda plus naught and that of the anion by lambda minus naught, then the limiting molar conductivity of electrolyte is molar conductivity lambda m naught equal to nu plus lambda plus naught plus nu minus lambda minus naught, where nu plus and nu minus are the number of cations and anions per formula of electrolyte. Degree of dissociation. It is ratio of molar conductivity at a specific concentration C to the molar conductivity at infinite dilution. It is denoted by alpha equal to lambda mc divided by lambda m naught. dissociation constant K equal to C alpha squared by 1 minus alpha, where K is acid dissociation constant, C is concentration of electrolyte, alpha is degree of ionization. Faraday's constant, it is equal to charge on 1 mole of electrons, it is equal to 96487 coulomb per mole, or approximately equal to 96500 coulomb per mole. Faraday's first law of electrolysis. The amount of substance deposited during electrolysis is directly proportional to quantity of electricity passed. Faraday's second law of electrolysis. If same charge is passed through different electrolytes, the mass of substance deposited will be proportional to their equivalent weights. Product of electrolysis. The product of electrolysis depends upon the nature of electrolyte being electrolyzed and the nature of electrodes. If electrode is inert like platinum or gold, they do not take part in chemical reaction, that is, they neither lose nor gain electrons. If the electrodes are reactive, they will take part in chemical reaction and product will be different as compared to inert electrodes. The electrode potentials of oxidizing and reducing species. Some of the electrochemical processes, although feasible but slow in their rate at lower voltage, this require extra voltage, that is over voltage at which these processes will take place. The product of electrolysis also differ in molten state and aqueous solution of electrolyte. Cells. A primary cell is a cell in which electrical energy is produced by the reaction occurring in the cell. For example, Daniell cell, dry cell, mercury cell. It cannot be researched. Dry cell adenose Zn2 Zn2 plus 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 electron at cathode MnO2 plus NH4 plus plus E minus 2 MnOOH plus NH3. The net reaction Zn plus NH4 plus MnO2 to Zn2 plus MnOOH plus NH3. Secondary cells, those cells which are used for storing electricity. For example, lead storage battery, nickel cadmium cell. They can be researched. For example, lead storage battery at anode Pb plus SO4 2 minus 2 Pb SO4 plus twice E. At cathode PbO2 plus SO4 2 minus plus 4H plus twice E 2 Pb SO4 plus twice H2. The overall cell reaction consisting of cathode and anode reactions is Pb plus PbO2 plus twice H2 SO4 2 twice Pb SO4 plus twice H2. On recharging the battery, the reaction is reversed. Nickel cadmium cell, it is another type of secondary cell which has longer life than lead storage cell but more expensive in manufacture. The overall reaction during discharge is Cd plus twice NiOH whole 3 to CdO plus twice NiOH whole 2 plus twice H2. Fuel cells at anode twice H2 plus 4OH minus 2 4H2 plus 4E minus. At cathode O2 plus twice H2 plus 4E2 4OH. The overall reaction twice H2 plus O2 2 twice H2O. Corrosion, the processes of slowly eating away of the metal due to attack of the atmospheric gases on the surface of the metal, resulting into the formation of compounds such as oxides, sulfides, carbonates, sulfates, etc. is called corrosion. For example, rusting of iron, development of green coating of copper and bronze. Prevention of corrosion: covering metal surface with paint or by some chemicals, for example bisphenol. Another simple method is to cover the metal surface by other metals such as tin, zinc, etc.